All right, welcome to the overview of the background sections of Lab 1. Let's scroll on down and take a look. So you can see Lab 1 is broken into two parts, Week 1 and Week 2. And all of the background sections, as well as a goals section and an equipment section, are included in Week 1. Now the way this works, it's an accordion format. So to see the text, just click on the blue bars and it will expand. Now if you open too many of them, the lab gets kind of lengthy and difficult to navigate. So I usually only open one at a time. The first one is the goals for Lab 1, and we don't need to spend any time on this because this is what we talked about in the introduction video. The next one is the equipment, and for this lab and for most of our labs, all you need is your computer and an internet connection. If you need anything else, it will be listed here. And then we have 5 background sections. The first 4 are on the prompt telescopes. These are the telescopes that my group at UNC Chapel Hill have built and deployed, and we have deployed them to some of the best and some of the darkest sites around the world. There are currently 5 different prompt sites, and 2 of these sites have multiple telescopes there, multiple prompt telescopes. And then background section B, we discuss the broader, greater Skynet Robotic Telescope Network. Skynet has 2 different types of telescopes. It has prompt telescopes, which again are the ones that we have built and are going to be uniformly the highest quality telescopes, the highest quality sites on the system. And then you have the partner telescopes. And these are telescopes that other people have built, and then they have come to us asking if they could put them on our network to take advantage of our scheduling capability, our scheduling interface. And we've done that, and we've grown Skynet to about 20 telescopes distributed around the world, and we integrate more all the time. Now the partner telescopes, some of them are very high quality and at very high quality sites. Others are at campus location, campus observatories, bright sky locations, not as high quality. So it's more of a mixed bag with the partner telescopes. When you're putting your observations in throughout this laboratory sequence, we're going to encourage you to limit yourselves to the prompt telescopes. But if time is running out and you're getting desperate, you can just put them on every telescope you have access to. And you'll have a greater chance of the image coming back in time. Okay, let's open up the first of these sections and take a look. This describes the various locations that we have built our prompt telescopes, and it focuses on our primary site, which is Cerro Tololo Inter-American Observatory at the Chilean Andes. This is the US government's observatory in the Southern Hemisphere. They lease the land from the Chilean government. There are many, many telescopes at this observatory, including the prompt telescopes. Here's a picture, shows you what it's like to be there at night, and the picture doesn't even do it justice. I've been there many times, and it's an amazing place to work. You're working on the telescopes and you look up and you can see the Milky Way, you can see the dust lanes, tremendous detail, more stars than you've ever seen before. So a great place to work and a great place to have telescopes. And I'm glad that we'll be able to share our telescope access with you as students. So that's a great opportunity. Now embedded in here, I have some fun links. This is a video that I'll let you watch the full thing on your own time, but how to build 6 telescopes in 60 seconds. These are the first 6 telescopes that we built, prompt telescopes. And we installed a webcam that took a picture every 10 minutes, and we pieced it together into a movie after the fact. We scroll down, you can see our second biggest site. This is at the National Observatory of Australia, Siding Spring Observatory in eastern Australia. We have a handful of telescopes there. Now, unfortunately, a few years ago, there was a lightning strike, and the strike damaged our mounts, and so this site is currently offline. I have raised enough money to replace the equipment. In fact, I have it all ready to go, and we're just waiting for COVID to abate. I'm taping this in 2020, and so we're not allowed to travel. But once we're allowed to travel again, we'll go to Australia and bring this site back online. Now, on the other side of Australia, we have another prompt site, the Meckering site. And also in Canada, we're opening 2 new prompt sites, one outside of Athabasca and one outside of Saskatoon. And all 3 of these sites, they're just a single telescope, and these are telescopes that have been redeployed from Chile. We've been upgrading our telescopes in Chile to larger telescopes, and so our smaller telescopes are getting redeployed to these other new prompt sites. So you'll have access to all 5 of these as you're carrying out the labs. Here we have a couple more links. This shows you what happens when the sun sets. This is, again, our primary site at Cerro Tololo. Once the sun is a degree below the horizon, the domes automatically open and the telescopes automatically move into position. And they begin the evening by taking pictures of the still bright sky. And we do that because it illuminates all the defects in these cameras and dust on the camera lenses. We then use these images to correct the ones that you take later in the night when the sky is dark. And Skynet does all of this for you automatically. There's another link here. This is a panable, zoomable webcam located also at Cerro Tololo, so you can explore the observatory. If I click here, we'll zoom in to the prompt telescopes. There's 6 little ones, and then 2 larger domes that we built later on. You can zoom into individual telescopes if you want, or you can zoom way out and see the surrounding environment. It's a very arid, mountainous climate and area. And here you see the ridge with all the small telescopes. You can also click on different parts of the image to pan and zoom around. And I'll let you explore the rest on your own, but there are also large telescopes at this observatory. It's a 2-mountain observatory, and the large telescopes are on the tops of these 2 mountains. And by clicking on different links, you can explore those as well. Okay, let's close this section. The next section describes why we built the telescopes in the first place. Although they're used by thousands of students every year now, they're also used by hundreds of researchers. And originally, we built the telescopes for a single research objective, and that is to study a type of cosmic explosion called a gamma ray burst. These are massive stars that have come to the end of their lives. They explode, producing gamma rays, and then the core collapses to a black hole. This is my area of research. Those gamma rays make their way across the universe, eventually to Earth, where we have gamma ray satellites in orbit that detect the gamma rays, and then they send the information down to us on the ground and to other telescopes around the world that then slew into position as quickly as possible, because these things fade very quickly, and take some pictures. We built Prompt initially, the array, the original 6 telescopes, as a distance measuring device for these gamma ray bursts. As a grad student, I was part of a paper that predicted that we would find these things farther out than anything else ever. Explosions anyway. And so then when I got to UNC Chapel Hill, I built this trying to find the most distant explosion in the universe. And we built the telescopes in 2004, and by 2005, we had done just that. We discovered the most distant explosion in the universe. It occurred 12.9 billion years ago, when the universe was only 6% of its current age. So these telescopes were originally built for research, but they're now used for more than just gamma ray bursts. We have hundreds of researchers who, in addition to gamma ray bursts, they study supernova explosions, supermassive black holes at the cores of galaxies, variable stars of every stripe, pulsating white dwarfs. Gravitational waves are detected by large government facilities, and we follow up those detections, looking for optical signatures. We study things closer to home as well. We characterize some of the new worlds that are being discovered out beyond Neptune. And with some funding from NASA, we characterize the orbits of asteroids, just to make sure they're not going to strike the Earth. So it does a great many different research and science activities in addition to being open to students for use. So it's kind of exciting. You've been given access to real telescopes at real sites that are used by real astronomers, and you'll be using the exact same facilities, the exact same interface to collect your data. Okay. The next section describes how a prompt telescope works. So here's a picture of one of our smaller telescopes. I know to many of you this might seem like a big telescope, a large telescope, but to a professional this is a small telescope. What makes it unique is that it's fully automated. That's what makes the Skynet telescopes unique. We scroll down here, you can see how the light works its way through the telescope, comes in through the top, down the tube, and this is actually a tubeless telescope. Most telescopes that you're accustomed to, there'd be a tube here that you can't see through. But since these sites, some of these great sites are a little bit windy, being up in the mountains, we got these telescopes special made to be completely open. The wind can go through them instead of pushing on them. If the wind pushes on them, you end up with the blurry image. Anyway, let's follow the light path. Comes down through where the tube would be, and then it strikes the primary mirror. And this is how we designate the size of a telescope. These are 16-inch diameter telescopes. That's referring to the primary mirror. The light bounces off and strikes a secondary mirror. It's on a little motor. We can move that in and out just a little bit, and that's how we focus the telescopes. And Skynet does that for you automatically. The light bounces off the secondary and then comes down through this tube called a light baffle. That prevents stray light, maybe from other buildings or maybe from the moon being up in the sky, from getting into the camera. It restricts it to just the astronomical light that you're looking at, comes down the light baffle through a hole in the primary mirror and down to the filter wheel and digital camera. I'll get back to them in just a minute, but the other component is the mount. And this is actually the most important part of the telescope, the most important part of any telescope. And that's because these telescopes, as you know, are sitting on a planet that's rotating. And if we want to image a part of the sky, these telescopes have to rotate at the exact same rate that Earth is in the opposite direction to cancel out that motion. So you want to have a high quality mount, because if you don't do this very well, you'll end up with a blurry image. And these are high quality mounts. Anyway, the light eventually makes it down to the digital camera, and these cameras are different. You have digital cameras built into your phone, many megapixels in color. These astronomical digital cameras, far fewer pixels. Kind of the telescope that you're looking at here, that camera, that's a 1K by 1K, so a 1 megapixel black and white camera. And again, you have many more megapixels on your phone and you have color, and we don't. And my camera that camera right there cost $10,000, $15,000. So why is it so expensive for so few pixels and only black and white? And that's because these cameras are designed to see in the dark. We're looking at things very, very faint. When you use your camera phone, you're normally taking pictures of things that are well lit. We're taking pictures of things that are quite the opposite. And so you pay extra money for that sensitivity, and you lose pixels, and you lose color. Now, you've seen many astronomical photos, and those are usually in color. So how do astronomers do it if our cameras are black and white? The way we do it is with a filter wheel. And you see that here, and here's an example filter wheel. This is a rather simple one. It has 3 filters, red, green, and blue. And so if we want to make a color picture, you put the red filter in the optical path, and you take a black and white picture of red light. And then you take another black and white picture of green light, and another black and white picture of blue light. So you have to take 3 pictures using 3 different filters, and then afterwards, in post-processing, you can combine them into a color picture. So most astronomical pictures that you've seen that are color were made in this way. Now, in this lab sequence, we will just be taking short exposures and black and white exposures. We're not going to be doing color images. The reason for that is it takes more time. It takes 3 times as long to get 3 colors. And often if you're imaging something faint, you have to do many, many exposures. And the goal of this curriculum is to serve thousands of students across the nation and across the world. And so we do that by making strategic use of the telescope time. We're just going to do short exposures, and these are going to be black and white exposures. That said, you've been given more than enough time to do the tasks in the lab. You should have some time left over. So if you want, you can go and try to make your own color image. You can pick some object, maybe a Messier object. These are big, bright objects, and image it in red, in green, in blue, and combine those images after the fact. But that's separate from the curricular materials. The last section on the prompt telescopes talks about their maintenance. And this is just to let you know that these are real telescopes working under real conditions, and they break. Now, Skynet is pretty smart. It knows of hundreds of already documented modes of failure. We have various different pieces of equipment. Each telescope is different, and they can break in hundreds of different ways, and Skynet knows hundreds of these ways and can correct most of them by itself, automatically. Now, occasionally something breaks that Skynet cannot auto-correct. In that case, it emails my staff and sends text messages, and we log on, and we can fix most things remotely. Occasionally something will break that requires a human to go to the telescope, and we'll interact with the staff at these observatories, and normally we can get things fixed within hours or days. Sometimes you have a critical failure, like a camera stops working altogether and it needs to be shipped back to the manufacturer, and a telescope can be down for months. But in these labs, when you submit your observations, you're never going to submit to just a single telescope. Well, very rarely anyway. Most of the time you're going to submit to as many telescopes as you have access to, or as many prompt telescopes as you have access to. So if one of them goes offline for an extended period, it shouldn't be a big deal. I should also say we make regular trips to the telescopes to do maintenance, and during these maintenance trips, the telescopes can go offline. And our last section just talks about Skynet more broadly. Again, we have prompt telescopes and we have the partner telescopes. And if you want to explore both, you can go to the main Skynet site. And under telescope sites, you can see all the observatories that are currently connected to Skynet. You can click on them and learn more about that particular observatory. This is Tololo. You can see here's the interactive webcam. And you can click on individual telescopes. Some of them have a webcam, and you can learn more about the camera that's attached, the field of view, the filters that are available, etc. Also, same link. Instead of going to telescope sites, you can go to Skynet Live, and that shows you which telescopes are connected right now. So you can see we have a handful of telescopes on right now. I'm shooting this in the middle of COVID, so a lot of our observatories are closed because of the pandemic, but we still have quite a few telescopes connected. And you can see if the sun is up or down, negative sign means it's below the horizon. You can see if the weather is good or bad, and you can see what the telescope is currently doing. Like here's the one in Meckering, Australia. The mount is slewing, and it's getting ready to take this observation. You can also see where they're pointed in the sky down here. Okay, that's it for this orientation video.